Hi, my name is Sung-Hoon Jang, and in this video, I will talk about fractals, Koch snowflakes, and calculations of the perimeter and area of the Koch snowflake behind it. In the past, most people believed that the geometry of nature was strictly based on simple objects such as straight lines, circles, and polygons. For example, the sun and the planets all appear to be spherical, and the planets revolve around the sun in an elliptical path. But many objects in nature are so complicated and irregular that we would not be able to model them with simple geometric shapes. For instance, what geometric shape could be used to model a tree or a mountain range? Of course, one could just use triangles, as was the technique in computer graphics about 10 to 15 years ago. However, this will not be a good representation of all the intricacies of the leaves on the tree or the jagged peaks of the mountain, and will look very unrealistic. Fractals are the appropriate tool for modeling these complicated shapes and patterns, yet they were not easily accepted by mathematicians at the time of their discovery over 100 years ago. They were categorized as irrational, and were generally considered to be of interest only to researchers who indulged in mathematical oddities and not to the real-world scientists. Fractals possess self-similarity. Self-similar objects appear the same under magnification. They are, in some fashion, composed of smaller copies of themselves. One example of fractals is Koch Snowflake. I'm sure I'm mispronouncing the Koch part, but this shape was found by Niels Fabian Hilge von Koch, which I'm sure I'm mispronouncing again. Anyway, to form the Koch snowflake, we start with an equilateral triangle whose sides are 9 units long. In the first iteration, an equilateral triangle with sides 3 units long is added in the center of each side of the original. In the second iteration, an equilateral triangle with sides 1 unit long is added in the center of each side. And then in the third, an equilateral triangle with sides 1/3 unit long is added in the center of each side. The following iterations continue this process forever and ever and ever. Now, let's explore the perimeter of the Koch snowflake. What do you think the perimeter would be if there were infinite iterations? The initial perimeter of the fractal will be 27 because there are 3 sides, each 9 units long. In the first iteration, their perimeter will increase by 9. Each successive iteration will thereby increase 4/3 of the increase from the preceding iteration. After nth iteration, the length of a side is 9 times 4/3 to the nth power because we start out with 9 on a side and increase 4/3 by each iteration. Thus, we can define a series to represent the perimeter of the Koch snowflake as follows. The initial perimeter is 27, and since we are adding up every possible additional area corresponding until nth iteration, we use the sigma notation to illustrate the series. Notice that the initial perimeter is 27. After the first iteration, there are 4 triangles with a total perimeter of 36. After the second iteration, there are 12 triangles with a total perimeter of 48. The perimeter of the snowflake increases after every iteration. Since this process has continued on to infinity without stopping, the perimeter of the snowflake is infinite. Mathematically, limit as k goes to infinity, 4/3 to the kth power is infinity, and hence 27 plus 9 sigma k equals 1 to n. 4/3 to the kth power is divergent. Next, let us explore the area of the Koch snowflake. The first observation is that the area of a general equilateral triangle with side length s is s squared times √3/4. The size of the additional triangles for each iteration becomes smaller and smaller. Note that the additional perimeter decreased as well, but still the total perimeter was infinite. Would the area increase to infinity, or would it converge to a specific number?
Created using Powtoon.